Chest X-rays are one of the most widely used imaging tools for diagnosing thoracic disorders. However, these disorders can be difficult to detect, even for experts. That's why we aim to support diagnosis by developing a CNN-based classification model to automate and improve the accuracy of identifying 5 key thoracic diseases. Our main stakeholders are radiologists who rely on accurate tools to assist their diagnostic decisions without being misled, and they rely on diagnostic accuracy, interpretability, and reliability of the model, as well as their reliability and accuracy of our system significantly influence their diagnostic outcomes, as well as patients who have to face the real-world consequences from errors. Misdiagnosis can delay treatment, while false positives can lead to unnecessary stress and procedures, with potential impacts of their emotional well-being as well as physical well-being, and lead to overall worse quality of life. This leads to our main research question, which is to what extent do modifications to the structure of a CNN-based chest X-ray classification system impact both model performance and ethical considerations in clinical deployment, with our technical sub-question being to what extent does implementing structural changes improve the F2 score of a CNN-based chest X-ray classification system across 5 target thoracic disorders compared to the baseline model, with our ethical sub-question being how do changes in type 1 and type 2 error rates resulting in CNN structural modifications affect ethical considerations in clinical deployment, particularly in terms of radiologist decision-making and potential patient harm or their delayed treatment. This leads into the ethical aspects that we've had to take into account, namely focusing on 2 key principles: minimizing harm and accountability. From a deontological perspective, which emphasizes moral responsibility and duty, our system was designed to help radiologists without replacing them. For instance, a misdiagnosis of pneumothorax could be fatal, so we use class weighting and prioritize the F2 score, which emphasizes recall and helps reduce false negatives. But prioritizing recall also comes at a cost: higher false positives, which might burden doctors and lead to overdiagnosis. So we need to carefully tune our models to help balance these risks. Choices like adding GradCam visualizations and focusing on modern interpretability were also ethical design decisions to ensure that doctors can understand and trust the model's prediction. In short, our objectives weren't just to build a high-performing model, but also one that operates responsibly in clinical settings, protecting patients, supporting doctors, and also ensuring ethical integrity throughout.
In this section, I will outline the key techniques and ideas incorporated into our deep learning model, the reasoning behind our choices, and how the system can be used effectively. For our model's architecture, we chose ResNet-50, a widely used convolutional neural network, which we employ to transfer learning on. This means the model has been pre-trained on ImageNet, which is a large dataset containing more than 14 million pictures of all kinds. ResNet-50 was mainly chosen for its proven effectiveness in image classification tasks, and specifically its ability to create residual connections, which basically act as pattern shortcuts between certain detected features in the output classes. The picture on the slide shows both the structure of the model and a rough example of some of the processing done to a scan. Next, we have our pre-processing strategies, which include the histogram equalization, enhancing image contrast and variability, shown in the first picture above, and image augmentation techniques like random rotation and flips. For example, type 4 of the second picture representing a little tilt in the form of degrees, and type 2 and type 1 flipping horizontally and vertically the scan. These help the model generalize better and minimize its bias. For fine-tuning, which is the process of adjusting various parameters regarding to how the structure learns and performs over each iteration, we tested everything while closely observing the training and validation errors to ensure they behave as optimal as possible. And every adjustment we made was motivated by either simple trial and error or taking inspiration from previous experiments done on similar disease detection tasks that required the same precision in regards to object detection and recognizing vital features. In the table below, you can see different hyperparameters and their corresponding results. For capabilities and pitfalls, the system can be definitely improved further towards better classifying output amongst all cases, but currently the model performs best when detecting if the patient is actually healthy, which is class 3 circled in the middle of the confusion matrix, but it also does quite well when classifying for atelectasis and effusion, class 0 and 1, circled in the top left corner of the matrix. And finally, for additional outputs, we have added confidence intervals that will provide a range for each class's predicted probability, indicating how confident the model's output is across different samples. This process will generate a distribution of probabilities for each class and final additional labels which would be assigned for each scan. We have also included an entropy evaluation, which would further show the uncertainty in these predicted labels. but more of them on the next slides.
Now let's move to the performance evaluation of our final model. Our evaluation relies heavily on the F2 score and accuracy. The F2 score is particularly important because it places extra emphasis on minimizing false negatives, which is critical for avoiding misdiagnosis in a clinical setting. Accuracy, on the other hand, ensures that our model consistently identifies lung diseases correctly. In addition to these metrics, we also monitor entropy distribution, which quantifies the model's uncertainty. A lower value indicates that the model is more confident in one particular class, while higher values indicate uncertainty spread across multiple classes. We also compute the mean predicted probability for each class, with 95% confidence intervals derived from a bootstrap procedure in order to understand how the model distributes its confidence across different classes. Finally, we use a confusion matrix to have a more granular view of performance than a single metric like accuracy or F2 score. This way, we can directly see whether the model tends to confuse similar conditions or if it is systematically struggles with a particular class. The overall performance of our final model indicates that both accuracy and F2 score are slightly above 40%. The confusion metric shows that for classes 2 and 4 there are significant off-diagonal values under predicted class 3. This suggests that the model frequently confuses these three classes with each other. For class 1 seems to have a relatively higher correct count compared to total samples, indicating that the model distinguishes class 1 better. Finally, for class 5 and 0, there is a broad spread of misclassifications across all the remaining classes. With this side-by-side overview of each class's performance, we can identify where the model is doing well, as is the case for class 1 and 5, and where the model room when there's room for improvement, in this case, class 2 and 3. The bars indicate that the model is allocating the highest mean probabilities to class 1 and 2, with class 2 having a tight confidence interval. Also, class 3 and 4 have tight intervals despite the fact that their mean probabilities are lower. This indicates that the model's performance is stable across multiple test samples. Observing the histogram, we can see that the bulk of samples have entropy values clustered in the 1.25 to 1.75 range, which means that for many cases the model's predictions are moderately spread out, implying it has some uncertainty when distinguishing between certain classes.
Now, how can this system be implemented as a clinical decision support system? After an X-ray of a lung has been made, it can be given to the system as input. After the image has gone through the earlier described process, the system will return a class probability distribution and a heat map that displays which areas were important for the system's resulting output. A radiologist can now take these results into account while setting up a diagnosis and possibly even share them with the patient if they want. This way, a radiologist can get an additional idea of the possible interpretation of the image, or, if they already had an idea, the system could back their idea up, increasing confidence for the radiologist to efficiently create a diagnosis. On the other hand, if the system spots something on the image that the radiologist might have missed, the probabilities could make the radiologist think twice and make sure that they are interpreting the image correctly. If results of the system are given to the patient as well, it could increase the patient's trust in the radiologist and prevent wasting time by seeking a second opinion from another radiologist so that they can get the treatment they require as soon as possible. However, these benefits could also turn into disadvantages if the system is wrong. This is why it is important to keep in mind that the system can make mistakes. The results shouldn't be treated as if they were made by an expert, they should serve as a guideline. Critical thinking should always be a part of medical decision making, especially when dealing with disorders that could be deadly. As long as this is taken into account, the system has the potential to improve healthcare around thoracic disorders for everyone involved.